Welcome back to the series. In the previous episodes, we completed our register, bit field, and GPR definitions. And more importantly, we explained what each one does and why we need them. Today, we're stepping into one of the most important topics in embedded systems, clock initialization. In this episode, we'll configure the ATSM3 X8E system clock to run at 84 MHz, exactly the way professional firmware does it, using only registers. This is where all those register definitions we wrote earlier finally come together and start to make sense. This part is critical because every peripheral, every delay, and every instruction timing in the system depends on the clock configuration. Let's get started. Before we dive in, one quick note. I've updated all references from EFC to EEFC in our code so everything stays fully consistent with the terminology used in the official datasheet. Now we start by defining a dedicated function for clock configuration. Static void board underscore clock underscore to 84 MHz. Void. It takes no parameters. This function is responsible for configuring the board clock to run at 84 MHz. To achieve that, we follow three clear and structured steps. Enable the external crystal oscillator, configure and lock the PLL, safely switch the master clock to the PLL output. The function is marked static because it is used only inside this source file, keeping the configuration local and prevents unintended access. Overall, this function has a single responsibility, bringing the MCU from its reset state to its final stable operating frequency. The first thing we do inside the function is define a key for the main oscillator register, or MOR. And here we say const uint32 underscore t MOR underscore key equals ckgr underscore MOR underscore key, and we pass in 0x37u. This key is required whenever we write to the MOR register. Without it, the MCU would ignore any changes to the main oscillator settings. Then we define the oscillator startup time. Const uint32 underscore t os count equals ckgr underscore MOR underscore MOS CX TST, and we pass in 0x8u. The MOS CX TST field represents a delay in slow clock cycles, and setting it to 0x8 gives the crystal enough time to start oscillating reliably before we try to use it as a clock source. According to the datasheet, the startup delay is calculated as this. The slow clock is a low-frequency clock about 32 kHz that runs independently of the CPU. This step is very important. If we switch to the crystal too early, the clock may be unstable. Before increasing the CPU frequency, we must configure the flash wait state. And here we say EEFC0 underscore FMR equals EEFC underscore FMR underscore FWS, and we pass in 4U. And EEFC1 underscore FMR equals EEFC underscore FMR underscore FWS, and we pass in 4U. At 84 MHz, the flash memory cannot deliver instructions in a single CPU cycle, so we add wait states. In this case, 4 wait states, or 4 extra CPU cycles, to give the flash enough time to respond. Next, we enable the external crystal oscillator. First, we check if it's not already selected like this. If PMC underscore CKGR underscore MOR and CKGR underscore MOR underscore MOS CSEL. Then we actually enable the external crystal oscillator by writing to the main oscillator register PMC underscore CKGR underscore MOR equals MOR underscore key or OS count or CKGR underscore MOR underscore MOS CRC EN or CKGR underscore MOR underscore MOS CX TEN. MOR underscore key unlocks the register, so this write is accepted. And OS count defines the crystal startup delay measured using the slow clock. This keeps the internal RC oscillator running during the transition. And this one enables the external crystal. Now we need to wait until the external crystal oscillator is fully stable, and we do that like this. While not PMC underscore SR and PMC underscore SR MOS CX TS. This loop continuously checks the PMC status register. Once the crystal is stable, we switch the main clock source to it. PMC underscore CKGR underscore MOR equals MOR underscore key or OS count or CKGR underscore MOR underscore MOS CRC EN or CKGR underscore MOR underscore MOS CX TEN or CKGR underscore MOR underscore MOS CSEL. Then we wait until the MOS CSELS bit becomes 1, indicating that the main clock switch to the external crystal is complete. And here we say while not PMC underscore SR and PMC underscore SR underscore MOS CSELS. Even though the datasheet says 0 means selection done, on real 873X8E hardware, the bit actually goes high when the switch is complete. Next, we set the master clock source to the main clock. PMC underscore MCKR equals, inside parentheses, PMC underscore MCKR and not PMC underscore MCKR underscore CSS underscore MSK and outside or PMC underscore MCKR underscore CSS underscore main underscore CLK. Here we first clear the previous clock selection bits and then select the main clock as the source for the master clock. And we need to wait until the MCKRDY bit is set, which means the master clock has finished switching and is stable. And we do that like this. Well, not PMC underscore SR and PMC underscore SR underscore MCK RDY. This intermediate step ensures stability before we configure the PLLA or apply prescalers. Now we configure PLLA to generate 168 MHz. PMC underscore CKGR underscore PLLAR equals CKGR underscore PLLAR underscore 1. This is a required constant that must always be set when writing to this register. Or CKGR underscore PLLAR underscore MULA, and we pass in 13U. This sets the PLL multiplier to 13, which multiplies the input clock to reach the desired 168 MHz frequency, or CKGR underscore PLLAR underscore PLL A count, and we pass in 0x3FU. And this defines the PLL lock time, giving the PLL enough cycles to stabilize before it can be used, or CKGR underscore PLLAR underscore DIVA, and we pass in 1U. This one sets the divider to 1, meaning no division is applied to the input clock before multiplying. And then we say while not PMC underscore SR and PMC underscore SR underscore lock A. And this loop waits until lock A is set, which indicates that PLLA has locked onto the target frequency and is stable. Now we apply a prescaler while still running from the main clock. PMC underscore MCKR equals. We first clear the previous clock source and prescaler bits to avoid affecting other settings. And to do that, inside parentheses we say PMC underscore MCKR and not, and again inside parentheses PMC underscore MCKR underscore PRES underscore MSK, or PMC underscore MCKR underscore CSS underscore MSK outside, or PMC underscore MCKR underscore CSS underscore main underscore CLK. This ensures we continue running from the main clock while adjusting the prescaler. This is safer than switching to PLLA immediately. Then we say or PMC underscore MCKR underscore PRES underscore CLK underscore 2. This one sets the master clock prescaler to divide by 2 and effectively reduces the 168 MHz PLLA output to 84 MHz, preparing a safe system clock frequency before switching to PLLA. After changing the master clock settings, we must wait until the clock stabilizes. While not PMC underscore SR and PMC underscore SR underscore MCK RDY. Finally, we switch the master clock source to PLLA. PMC underscore MCKR equals. We first clear the previous clock source bits. Inside parentheses, PMC underscore MCKR and not PMC underscore MCKR underscore CSS underscore MSK, or PMC underscore MCKR underscore CSS underscore PLLA underscore CLK. This selects PLLA as the new source for the master clock. After this assignment, the CPU will run at the PLLA frequency 168 MHz divided by any prescaler we applied earlier. And now we must wait until MCK RDY is set before proceeding to ensure the master clock is stable. While not PMC underscore SR and PMC underscore SR MCK RDY. The system is now running at 84 MHz safely and reliably. And that's it for this episode. We took full control of the 8730X8E clock system from scratch using pure C and direct register programming. No libraries, no shortcuts. In the next episode, we'll put this clock to work by building our own delay function, and we're also going to toggle the LED. If you enjoyed this deep dive, smash that like button, subscribe, and drop your questions in the comments. I love seeing your progress. Thanks for watching, and I'll see you in the next episode.